Okay, in this lecture we're going to talk about making predictions about positions using average velocity. So let's define the average velocity. The average velocity is a vector. We're going to construct the average velocity by looking at the change in position in a given time. So let's look at a vector, set of vectors. Let's say my position starts here. This is vector initial, R initial. And this is where I end up. So I'm starting my position here. I'm ending my position here. This is R final. And so R final minus R initial is equal to delta R. And here's delta R. Also a vector. Okay, so that's our construction. That's how we're going to start with this. Here's my delta R vector. These are both vector quantities, so they should wear hats. Now, the average velocity, V average, over some time interval is going to be given by R final minus R initial over time final minus time initial. That's the definition. And so V av is equal to delta R over delta T. So in a given amount of time, I've changed my position from here to here. My position is always defined on my coordinate system by my vector. I went from here to here in some interval of time, and I can calculate the average velocity given that. Now what I'd like to do is look at this equation here and try and expand that equation into another form. So let's do that. Leave our vectors here. So now I'm going to rewrite this equation by bringing things to the different sides of the equal sign, and I'm going to write that R final minus R initial is equal to V average. Remember, we preserve vectorness times T final minus T initial. Okay, so that's great. Does this make sense? I think it does. I think there's a preservation of units. If we look at the units on the left-hand side, there's units of distance. So this has units of length. This has units of length per time. This has units of time. And so we've preserved our units on both sides of the equation. Okay, so that's good. That's a good check. Okay. Now, let's go a little bit further. Let's put our final position equal to our initial position. I've just added R initial to both sides, plus V average times T final minus T initial. And so I can just simplify my delta T to look like the following. So, what does this provide us? This is what's known as an update equation. And if you're confused at all by this vector-like characteristic of this equation, I'm just going to rewrite it in component form so you can see it in its full component glory. So I'm going to assume that these are three-dimensional vectors. So this will be R final in the x direction, R final in the y direction, R final in the z direction. Those are all the components. That's equal to r final, or I'm sorry, r initial x, r initial y, and r initial z. And then I have v average, I'll just call it VA sub x, VA sub y, VA sub z times the scalar delta t. So if I want to solve this equation, I would solve each individual component, and then I would have three separate equations that I'm actually solving. So don't get confused by the fact that you have these vector quantities. They really just break down into their component forms. Okay. So we can do that for clarity. So let's write down every equation, just so it's clear. So the x final, that's going to, oh, I'm sorry, I was calling those r. Let's call it r in the x direction, initial, final, is equal to r in the x direction, initial, plus v average in the x direction times delta t. And notice I haven't put any scalars here. These are just the components. Ry final, r y initial, v av y, delta t. Rz final, rz initial, put some commas in here, make it clear, plus v av in the z direction, delta t. Okay? So that's how you would solve for each component, and then you would have your vector